Welcome back, class. So today I want to start talking about how to name compounds. And the first type of compound that we're going to look at are ionic compounds. So let's start here with the question of what ionic compound would form between K and S. Well, let's think about what we need to know in order to do this. Well, first of all, we have to know what K and S are, right? So we have to know our name symbol recognition, right? So we know K is potassium and we know S is sulfur. The other key thing that we need to know, right, is because this is a compound between a metal and a nonmetal, right? We got potassium, a metal, sulfur, a nonmetal. We can know that it's going to form an ionic compound. So to form an ionic compound, we have to know what ions these are going to form. And this is where we go back to some things we talked about in Chapter 2, where based on the location in the periodic table, we can predict what certain groups of elements, what type of ions they're going to form, because their goal is to lose or gain electrons to become like a noble gas, right? So if we look at this and we look at potassium on the periodic table, we know that potassium is an alkali metal. It's in group 1. And so it's going to form a potassium positive 1 ion. Right? It's going to lose that 1 electron to become like a noble gas. And sulfur is in group 6. So elements in group 6 will form a 2 minus charge, or in other words, they'll gain 2 electrons to become like a noble gas. So once we have the ions here, we can now put it together. And now remember, when we put these ionic compounds together, we always want to put together the simplest neutral formula. And so if I have a positive 1 and a negative 2, well, I can tell that I'm going to need 2 of the positive 1s, or 2 of the potassium positive 1s, to match up with the 2 minus on the sulfur charge. Now, another way that we can do this, especially if we get a little more complicated, this little shortcut, is you can take the charges and we can do this crossover thing, right, where the charge becomes the subscript of the opposite. So where sulfur has a charge of 2, that means K will end up with a subscript of 2. And with K having a charge of 1, then we'll end up with only 1 sulfur. So we end up with a formula of K2S, right? And again, this is the same way, either way we do it, right? We have 2 potassium positive 1s, gives me a total of positive 2, and 1 sulfur 2 minus gives you a total of negative 2, and they cancel each other out. So how would we name this then? So we have the formula K2S. Well, we have a system of naming here where the metal, or the first element, the cation, is we're just going to use the name of the element, right? The name of the cation. So in this case, it's just potassium. And the second element is going to be named by using the name of the anion, or the nonmetal typically, but we're going to change the ending to an IDE. So sulfur becomes sulfide. So in this case, we remove the last 2 letters and we change the ending to an IDE. Now, when we think about these nonmetals and they're going to change their endings to IDEs, there's a set of, common ones that are listed in the book, and the more you use them, the more familiar you'll become one. So we just saw that sulfur is sulfide. The halogens are pretty straightforward, right? We're going to remove the INE and add IDE, so we get things like chloride or bromide, etc. Oxygen is a little bit different. So oxygen becomes oxide. Nitrogen becomes nitride. And so the more we use these, the more familiar we will become with them. So let's do some practice of naming these simple ionic compounds. So we have the compound between sodium and nitride. So again, we have to know what charges they form. So sodium, right, being in group 1, is going to form a positive 1 ion. Nitrogen, well, look at nitrogen, that's in group 5, right? It's going to gain 3 electrons and form a 3 minus ion. And so if we cross these over, we end up with 3 sodiums and 1 nitrogen, right? Where we have 3 positive ones to give me a positive 3 to balance out my negative 3. And so we have a formula of Na3N, and this name becomes sodium nitride. Now we got magnesium and bromide here. So the magnesium ion that will form, so if we look at magnesium, we see that it's in group 2, right? So group 2 is going to form a 2 positive ion, and bromine is in group 7, the halogens, right? They are going to form -1 ions. Again, if we cross them over, we end up with 1 magnesium, 2 bromides, and we get a compound that's named magnesium bromide. Last one here, we have aluminum ion, right? Aluminum is in group 3, right? So it's going to form a positive 3 ion, right? It's going to lose those 3 electrons to become like a noble gas. And we got oxygen, it's in group 6. It's going to form a 2 minus, just like we saw with sulfur above, also in group 6. So if we do our crossover, we get Al2O3, and our compound takes on the name of aluminum oxide. So, we've looked at naming some simple ionic compounds. Now, one of the things I want to point out is that all of these metals that we've worked with so far, and this is going to be principally the group 1, group 2, and group 3 metals, will always form the same charge, right? Group 1 will form positive 1, group 2 will form positive 2, group 3 will form positive 3. Now, if we are working with other metals, right, we'll see that they will often have different charges they form, so we have to use a little different system. So let's look at that. So just to point out, the metals that will form always the same charge, right, are our alkali metals that form a positive 1, our group 2 alkaline earth that form a positive 2, our group 3 metals, which is really just aluminum, which will form a positive 3. Now, all our other transition metals and some of these lower main group metals down here, like lead and tin, these down here, and all of our transition metals, they can form multiple charges. Now, there are 2 notable exceptions that I do want to point out that it will help if you become familiar with, and that is zinc and silver. They are the 2 notable exceptions of the transition metals that always form the same charge. Zinc is a 2+, silver is a positive 1. So, for any of these metals, we can use that simple naming system that I just pointed out, that we just practiced. But what if we have one of these other metals how do we know what the charge is, right? We can't predict the charge based on the location in the periodic table. So how do we do it? Well, we can predict the charge on the metal by the nonmetal, and we can identify the charge in the name by adding one extra part to our name. So we're still going to have the name of the first element, typically the metal, by just using its name, but then we're going to add the charge on that metal using Roman numerals. And then we're going to write, again, the non-metal with that ID ending at the end. Now, of course, the reason we need to do this is because if a metal can have multiple charges, then it can form multiple compounds, right, with the same element. So iron and sulfur can combine in these two different compounds. Well, we can't name these the same, so if we were using our simple naming system, right, these would both be called iron sulfide. But, of course, they're not the same compound. So how do we distinguish them? So let's take the first one here, FeS. So first thing is we need to establish the charges of the ions. So in this compound, the key is the negative ion, right? We should always be able to know the charge on the negative ions based on where their location in the periodic table is. So we know that sulfur is going to form a 2- ion. Now that means the one iron that's in this formula, because again we have to be neutral, is going to have a 2 positive charge. So when we write out the name for this, I'm going to write it as iron, but then I'm going to include the charge in parentheses as a Roman numeral. So Roman numeral 2, so iron 2, and then sulfide in the same way. So let's take our second compound, Fe2S3. So again, if I look at this one, now I know that sulfur again is going to have a -2 charge, or 2- charge. So what does the iron have to be to balance it out? Well, if we look carefully at this, right, we have 3 of these, so we have a total negative charge of -6. So that means I need to have a total positive of +6. So that means I have 2 irons to split up this +6 charge. So that means each iron must be a 3 positive charge. So we have 2 +3 irons give me +6, and then 3 -2 sulfurs to give me -6. And so the name of this becomes, again, iron, but this time 3 sulfide. So the way we distinguish between these two compounds, right, is by putting the Roman numeral of the charge. So we have either iron 2 sulfide, which is this compound, or iron 3 sulfide, which is this compound. So let's do one more example using 2 compounds of copper and oxygen. So our first one, Cu2O. So if we, again, start with the negative charge, and we know that it's going to be a 2- for oxygen. So I have 2 coppers that have to give me a +2, so that means each one must be a +1. And so if I then write out the name, I have copper with the charge of 1, oxide. Now if I go to the next one, CuO. So in this case, it's still a -2 on the oxygen, right? So that means the one copper that it's paired with must be a 2 positive. So this one, right, is going to be named copper 2 oxide. So when we're dealing with a transition metal, or metals that can have more than one charge, we use the same basic naming system, same basic strategy, except we include the charge on the metal as a Roman numeral to distinguish one from the other when we write the name. Okay, earlier on I mentioned polyatomic ions. Now, we have a list of these. So this is the same list out of your book, and I wish I could give you a shortcut, but in order to functionally work with these, we need to memorize them, right? So with the ones in this list, we need to know the name, the formula, and the charge, right? So eventually, you need to be able to recognize, say, the NO3 minus ion as a nitrate ion. Or if I say the nitrate ion, you need to be able to say, it's NO3 minus. Right? So remember, these polyatomic ions, they're groups of ions, so groups of atoms, more than one atom, polyatomic, that are charged, right? So it's a grouping of more than one, and these are going to be more than one atom, which as a collection has an overall charge. And we treat these as a group. So when we put these into compounds, we treat them as a group, just like we would an atomic ion, right? So we don't have to name each particular atom, we name them as a group, right? Now, one thing that will be a slightly different here is that we don't change the name when part of an ionic compound. So you'll notice that almost all of these are negative ions, right? So they're going to go on the second. They're going to be the second part of our name, right? We're going to name the anion. And we've traditionally changed the name of the anion to IDE, right? And we do that with atomic ions. But we do not do that when we're doing polyatomic ions, right? If the name is nitrate, well, we use the name nitrate. Now, I will point out that there is one positive polyatomic ion that would replace the metal in an ionic compound, and that is the ammonium ion. So let's do a couple examples here. So let's look at CaSO4. So again, we use the same sort of strategy. The first key thing here is we need to recognize the existence of a polyatomic ion. Now the easiest way to do that is that if you look at all the compounds that we've named so far, they contain two elements, right? The positive ion, the negative ion, right? NaCl, or just two different ions. Immediately I see this and I have three different elements here: calcium, sulfur, and oxygen. That's my clue that I have a polyatomic ion, right? And I can identify that polyatomic ion as the SO4 ion. And at this point it becomes, again, knowing what they are, right? So just like I did with the other ionic compounds, we're going to look at the materials and see what charges we know. Now, in this case, we do know what the metal is, right? It's calcium, and we know calcium is in group 2, so it's going to always form the calcium 2 plus ion. Now, eventually, we'll know that SO4 minus, if we look here in our table, right, is the sulfate, or the SO4 with a 2 minus charge. Now, we can see that this makes sense, right? Because we have one calcium and one sulfate, so it makes sense that they have the same charge. So when I go to name this, I'm just simply going to call it calcium. Now, I don't need a Roman numeral because it's one of my group 1, 2, or 3 metals. And so I'm going to name the positive ion, name the cation, and then I'm going to name the negative ion. And again, I'm not going to change the name, so I'm just going to call it calcium sulfate. So let's try another one. Let's do FeNO3 2. Okay. So this one becomes a little bit trickier in the sense that if we look at the metal, right, it's a metal, it's a transition metal, right? So we don't immediately know the charge. So we really do here have to know the charge on my negative ion, in this case the polyatomic ion here, in order to finish this compound. So I'm eventually going to know that NO3, right, is nitrate, and nitrate is NO3, is NO3 with a -1 charge. So if I look at my compound, I have 2 of these, which gives me an overall -2. So that means the iron, to balance out, must be a +2 charge. So now I can go ahead and write out the name. I have iron. So it's a transition metal, so I'm going to have to use a Roman numeral. So iron 2, nitrate. So, same rules essentially that we follow for naming any other kind of ionic compound, except when we put in the polyatomic ion, we don't change the name. And we're going to need to put in the effort, right, to memorize these, right? I try to really minimize the stuff that you have to memorize. It does tend to be stuff that come at the beginning, so you're memorizing certain names and symbols. You're memorizing what charges certain groups form. We're naming polyatomic ions, but the key is we put in the work to learn them now, and then as we go to work with, again, naming and then chemical reactions and other things, that we immediately start to recognize these things. I would highly recommend flashcards for these. It tends to be a very, useful tool to just get that name of the ion formula with the charge. Get those 2 pieces together. So one last type of ionic compound that I want to touch on, and these are what are called hydrated or hydrate compounds. And these are simply, a hydrate is simply an ionic compound that contains a specific number of water molecules per formula unit. In the crystal structure. So there's actually water inside the crystal lattice with so many waters per formula unit of that ionic compound. The anhydrous, when we use the term anhydrous, this is no water, right? So the water has been removed somehow, right? So we'll do a lab on this where we dehydrate a compound and we heat it up and we go from the hydrated compound to the anhydrous. And if you look here at these pictures of this cobalt compound, we can see that the hydrate is a reddish compound, and the anhydrous is a purple. So by removing the water, we've changed the structure a little bit, and it turns it into a compound that doesn't necessarily behave differently in terms of its chemical properties, but has a different physical appearance, right? It's a different color. But how do we name these? So let's just look at this one. So here's our compound. So we're going to name the ionic compound part of this just like we would any other ionic compound. So we're going to have the cobalt here and the chloride. So we can easily recognize that the chlorine is going to have a -1 charge. And the cobalt, since we have 2 chlorines per cobalt, it has to have a 2 positive. So we have cobalt 2 positive, Cl minus as our 2 ions. So cobalt again is a transition metal, so we're going to have to put the charge in the name. So it's going to be cobalt 2 chloride. Now, the only difference here is we're going to add another part of the name to reference the water molecules. Now, we're going to do this by using prefixes to specify how many waters we have. So the prefixes we're going to use are, I'll list them here. So hemi would be if we had a half here. We have mono for 1, di is 2, tri is 3, tetra is 4, penta is 5, hexa is 6, hepta is 7, and octa is 8. And you shouldn't really go beyond that. So if we look here, we have 6, so that's hexa. So we add on here hexa hydrate. So we have one part of the name, which is cobalt 2 chloride, and then space, of course, hexahydrate would be the name of this compound. Okay, let's do one more just to close this off. Let's say we have this compound. So CuSO4 5 water. So again, we need to specify what these are. So we recognize, polyatomic ion. So the 2 parts, the 2 ions here I have are a copper ion and the SO4 ion. Remember this, the sulfate. So once we know what these are, right, we know the sulfate is a -2 ion. So we know the copper, because it is 1-to-1, has to be copper 2+. So now we have the charge on the copper, so we can now name it. So we have copper 2 sulfate, and then 5 waters penta hydrate would be the name. Okay, so hydrate compounds. So this covers all the types of ionic compounds we could possibly name. And I will sort of forewarn you that ionic compounds are probably the most, let's say, complicated, the most different variables here in terms of naming. The other 2 types of compounds that we're going to name, molecular compounds and acids, are a bit more straightforward in following a very specific scheme for the kinds of compounds. So we'll touch back here and talk about molecular compounds and acids.